Hello everyone, so welcome to this last part of isomerism, optical isomerism. So optical isomerism shown by those compound which having same molecular formula, same structural formula, but different optical activity. So to understand optical isomerism, little bit we will discuss some of the basic terms like chiral center and symmetricity. So chiral center is that sp3 tetrahedral atom attached to four different types of atom or group of atom. Then that center is called chiral center. And this molecule we can say chiral molecule. So here in question it is asking how many chiral centers are present in 2, 3, 4 trichloropentane. So here we can see that this carbon is connected to chlorine, connected to this side methyl group, connected to hydrogen, and along with that this group of atom. Similarly here this one is also chiral center. Here this carbon we can see this carbon is connected to hydrogen, chlorine, and two set of group of atom is same here, this one and this one. So this carbon having plane of symmetry. So such type of chiral centers are called pseudo-chiral. So total here chiral centers are 2 plus 1, 3. Pseudo-chiral center is also considered as chiral center. Means it having optical activity. In this compound, how many chiral centers are in the following compounds? So here you can see this carbon having hydrogen, methyl, ethyl, and this group of atoms, right? So, and along with hydrogen this is chiral center. Similarly this is also chiral. In simple way we can understand chiral center. Just you draw one line. If left hand side and right hand side different group of atoms are there, including hydrogen, then it is chiral center. Similarly here also chiral center, here also chiral center, here also chiral center, here also this one is chiral center. So total 6 chiral centers are there. Now stereo center. So we know stereoisomer are two types. One is conformer and one is configurational. So conformer isomers are not true isomer. So stereoisomers, in that only we will consider configurational isomer, that is geometrical and optical. So geometrical isomer along with that chiral center will give optical isomer. So here geometrical center 1 and chiral center 1. So total stereo center 2. Similarly here 3 stereo center. Now we will discuss optical activity. So those compound which show optical isomerism, they will have, like we discussed, definition, molecular formula same, a structural formula same. What will be different? Their optical activity phenomena will be different. So here let's suppose that simple light source bulb is there, which is giving unpolarized light, which is three-dimensional light. When it is passing through one instrument which is called polarizer, so through polarizer after passing this became one directional light which is called PPL light, plane polarized light. And now this PPL light is passing to long glass discharge tube in which organic solution is filled. So when this PPL light is passing and without deflected, if on this screen analyzer, if it is coming out, then that organic compound is optically inactive, means it will not show optical isomerism. But if light is going and it is deflected with clockwise or anti-clockwise with some angle theta, which will be analyzed on analyzer, then that compound is optically active. So let's see this one through one video illustration. So now here we can see that this is the source of light, this is polarizer, and this is the long glass tube where organic compound will be filled. And this is the analyzer where we will analyze the deflection of PPL light. So this is the source of light. When it is passing, it will give unpolarized light. And this unpolarized light, when it is passing through this polarizometer, So now it will become one dimensional light, that is PPL light, plane polarized light. Now this is passing to this long glass tube. So here we can see that some deflection happen, which is analyzed on the analyzer. So which is analyzed on the analyzer. So suppose if that plane polarized light going through this and if deflected clockwise, then that organic substance is called dextrorotatory. And if plane polarized light is rotated anti-clockwise with some angle theta, which will be analyzed on analyzer, then that organic compound is called levorotatory. In both cases, they are optically active. They will show optical isomerism. Here that observed rotation of PPL depends on the amount of substance in the tube, length of the tube, temperature, and as well as the wavelength of the light which is passing. One small topic we will study, a specific rotation. So a specific rotation is that rotation caused by 1 gram per ml of solution, organic compound solution, present in 1 decimeter length of the polarimeter at a specific temperature and fixed wavelength. So this alpha is theta by C into L, where theta is observed angle on analyzer, C is the concentration of solution, and L is the length of the tube. Length measure in decimeter, concentration we will take in gram per milliliter. So on behalf of this, here we have one question, that when an optically active compound is placed in 10 decimeter tube, is present in 20 gram of 200 ml of solution, which rotates PPL by 30 degree, calculate angle of rotation, a specific angle of rotation, if above solution is diluted to 1 liter. So a specific angle of rotation is constant. Its intensive property, like here you can see that it depends only on per gram per ml of solution in 1 decimeter length. So here we can see that alpha is equal to theta observed is 30, 20 gram present in 200 ml into length of the tube is 10. So alpha is coming 30. Now if solution is diluted further, then alpha observed will be changed, not a specific rotation, because it is per gram that 1 gram ml, 1 gram per ml in 1 decimeter. So now alpha is 30, so theta nu, since 20 gram of organic solution diluted to 1 liter, length of the tube is 10. So next alpha observed is 6 degree. Means on dilution that deflection of plane polarized light will be less. Now second basic term we will study, symmetricity, by which we can understand any organic compound is optically active or not, because every time we will not keep that organic compound in polarizometer and we will pass plain PPL light. So by symmetricity also we can understand that compound is optically active or inactive. So first here that symmetrical term is that POS, plane of symmetry. So if any molecule, if it is bisect and their equal part, half part is mirror image of each other, then that symmetry is called plane of symmetry. So like here one molecule can have more than one plane of symmetry also, like here plane of symmetry. If we are cutting from here, so this hydrogen and chlorine also will be cutted half and half, and this side also half and half, because atom is considered like a sphere. Similarly here also half plane of symmetry there, here also plane of symmetry. Here we can see benzene, so across carbon 3 plane of symmetry, and in between carbon 3 plane of symmetry, and one each slice also we can do, like this we can cut. So total it having 7 plane of symmetry. Second symmetrical element is that center of symmetry. So center of symmetry is what? If molecule having center of symmetry, it will be only one, not more than one. So like here, suppose from this center, diagonally opposite direction if we are moving, and if same group of atom we are getting, then it is having center of symmetry. So here down COH, so here up COH diagonally. Here CH3 up to diagonally down CH3, and similarly hydrogen. So it having center of symmetry. Similarly, this one also having center of symmetry. Similarly, this one also having center of symmetry. If any molecule having plane of symmetry and center of symmetry, then it is optically inactive. It will not rotate PPL light. If still one also symmetry is there, either center of symmetry or plane of symmetry, in both cases it is optically inactive. When both are not available, then only that compound will be optically active. Additional to also symmetrical element we will study axis of rotation. Axis of rotation is what? When that molecule you will rotate by certain angle with certain axis. So after rotation, that orientation of molecule which will come, that is the mirror image, means that is 100% it will overlap this one. So here we can see if one rotate the molecule by 360 by n, then new position of molecule is superimposable to original one, means this one will superimpose 100% this molecule. So here, since this molecule we are rotating by 180, so this CH3H will come this side and this CH3H will go this side. Now this one you can see is superimposable on this. So by rotation 180 means 360 by 180 is 2, means this molecule having C2 axis of symmetry, right? So one molecule could have more than one axis of symmetry, like benzene having C2 axis of symmetry, C3 axis of symmetry, and so on and so forth. Now alternate axis of symmetry is what? Alternate axis is that if this molecule is rotated with certain angle through one axis, so this molecule which is coming after rotation, its mirror image and this one will be same. Like here it is telling that imaginary plane around the rotational axis, rotation by angle x gives mirror image, means after rotation that this one is the mirror image of this molecule. We can say this one also, or we can say that its mirror image will be identical to this. Both statements are same. Now moving further, in odd member cyclic ring, always remember center of symmetry do not exist. Plane of symmetry might be there, but center of symmetry do not exist. Like here, let's suppose center of symmetry we are assuming. So bromine is diagonally opposite, hydrogen is diagonally opposite, this carbon is also diagonally opposite, but this carbon is not there here. So always in odd member ring, COS not present always. Now since we discussed 3D molecule to represent sp3 molecule, to represent in 2D projection, so we discussed dash wedge representation, we discussed after that Sohers representation, then after we discussed Newman projection. Now we will discuss one Fischer projection, and this only we will utilize for optical molecules. Means for molecule we will draw its optical that Fischer projection. So in Fischer projection, what? Dash wedge could be different orientation. It depends on the observer. So like if sp3 molecule is there, so in that if two atom, a group of atoms, if it is in plane, so two will be above and below the plane, dash and wedge. Another way also we can do, if we'll rotate little bit molecule, so it will look like this. This is also sp3 orientation, where two atoms are towards the observer and two atoms going away from the observer. So this two, so here always draw, what it is telling, that rule, always draw carbon chain in vertical line with highest IUPAC priority group or functional group, top or closer to the top. Means that vertical line should be include maximum number of carbon chain, means it should be longest carbon chain, and highest priority functional group and all should be near or at the top of that vertical line. And draw horizontal lines, how many chiral centers are there, and then after observe chiral center in that two bonds towards the observer, left and right. This one towards the observer, this is dash wedge, so it's only Newman projection. So here you can see this is the dash wedge, so that dash wedge only, this dash wedge only we can represent now in this Fischer projection. So in Fischer projection, always you should see that these atoms are coming towards you and these two are going away from you. Like here, that this is the Fischer projection. So this is the longest carbon chain, and highest priority of functional groups are near to the top. And this long vertical line, we know that it is going away from us, and this line, horizontal lines, are coming towards us. Horizontal line will be as much as many chiral center. Suppose if this is not given like that, if it is given traditional dash wedge representation, so you can, observer can stand here. So right hand side what is coming? H, and left hand side Cl. So right side H, left side Cl. So it having chiral center. Similarly, if suppose this observer is coming here, and it can see from this side also. So if observer is here, so you see this center, along with that from this side only you see this center, don't change your position. So from here, if observer is seeing, so right hand side OH, left hand side H, and here left hand side HCl, right hand side H. So this is Fischer projection for from the dash wedge. Now moving further, we understood how to draw Fischer projection. Now that how to know that any compounds is optically active or not. So case by case we will study that. First, if one chiral center is there, means that compound is always will be optically active. If compound having only one chiral center, means that tetravalent, in that all ABCD are different, means it is optically active compound. If more than one chiral center are present, then in that case, if compound is acyclic, then always you check by POS. Without checking COS also, you will get the result. So if POS is not there, means that compound is optically active, and if POS is there, then compound is optically inactive. So here we can see that in this, here plane of symmetry there. So such type of compounds are called identical or meso compounds, means this compound is optically inactive. No need to check COS in acyclic more than 2 center. So here we can see that again more than one center is there, so 2 center, and it having plane of symmetry is not there. Why? Because here bromine is there, here OH is there, so this compound is optically active. So more than one chiral center, in that if compound having plane of symmetry, then it is meso or identical compound and it is optically inactive. If it is having no plane of symmetry, then it is optically active. It will rotate ppalide either depending upon its nature, LIBO or dextro. Next, third case, if molecule is cyclic and that ring is odd. So we know that in odd ring, COS does not exist. So only we will check POS. So if POS is there, then it is optically inactive. If it is not there, then active. So like here plane of symmetry is there, so it is optically inactive. Here plane of symmetry is not there, because here methyl is there and here hydrogen is there. So this is optically active. Next, if molecule is cyclic and even ring is there, so we have to check both plane of symmetry and center of symmetry. In sequence you check, first you check plane of symmetry. If it is there, if one also there, then it will be optically inactive. If one is not there, then you have to check COS. So if COS also not there, then compound will be optically active. So like here plane of symmetry only there, so no need to check COS, so it is optically inactive. Here plane of symmetry is not there. Why? Because one methyl is up, whereas one methyl is down. So plane of symmetry is not there. Then we will proceed for center of symmetry. So center of symmetry, if here diagonally up, so here diagonally down should be there. So COS is not there. So both are not there, means this compound is optically active. Next, moving further, this compound we'll see. So like here, that plane of symmetry is there, right? So if one is also there, it will be optically inactive. Now here we can say plane of symmetry is also there. So suppose additionally we are checking COS, so diagonally opposite. So yes, even one is also there, it will be optically inactive. Now coming that, as we studied, that if molecule having one chiral center, then that compound will be always optically active. But it does not assuring that if any molecule having chiral center, which is also called asymmetric carbon or asymmetric center, then that molecule will be chiral. That molecule will be chiral means optically active. No. As we discussed that even though two chiral center is there, if molecule having plane of symmetry in acyclic molecule, then it is optically inactive. So like here we discussed that if molecule having chiral or asymmetric carbon, it may or may not be chiral molecule. Like here we discussed meso compound was having plane of symmetry and it was optically inactive. Once again you can see here, if molecule having chiral center, it may or may not be chiral means optically active. Like here this molecule having chiral center but it is optically inactive. It will not rotate ppalite because it having plane of symmetry. Here chiral center is there and this is optically active. So may or may not it will be optically active. Chiral center does not assure that molecule will be optically active. It may be or may be not. Next, another one, if molecule does not have chiral center, does not mean it will be optically active. Like here we can see that this all those, it does not have chiral center, they are not sp3, and we know that cumene or that that conjugated double bond. So here that this double bond is and this double bond both are, so this will be perpendicular, this will be perpendicular, so it neither having plane of symmetry nor it having center of symmetry. Similarly here, instead of one double bond, that instead of cumene or allene conjugated double bond, instead of one double bond, here ring is there and along with that double bond. So again this will be perpendicular, and this, if it is, suppose this is in plane, yeah, this is in perpendicular, so this is in plane. So now neither it having plane of symmetry or center of symmetry. Similarly this one also, and here due to Sir effect also it is, so it does not have chiral center, but even though it is optically active because neither it having plane of symmetry nor it having center of symmetry. Now moving further, absolute configuration. So absolute configuration is what? That RS configuration. So the actual 3D arrangement of group of molecules containing asymmetric carbon means chiral center is termed as absolute configuration, where R is rectus, which is clockwise, and S is sinister, anti-clockwise. Means this RS is just naming for that 3D molecules which is optically active or inactive, depends upon that. Any molecule we can give its naming or configuration RS and R and S. So Fischer projection, in that only we will do RS configuration. So first you apply CIP rule, which already we studied, that priority directly proportional to atomic number, then after atomic mass, and then after that if one atom is same, then see the three set of atom. If multiple bonds are there, then create dummy atoms, and cis and trans, in that cis is major. That all those priority wise we discuss. If fourth atom, here one additional, if fourth atom is on horizontal position, then always flip the answer. Means if it is coming clockwise R, then change it is to S. So like here we can see this Fischer projection. In that we know that these two are coming, means horizontal lines are coming towards observer and this is going away from the observer. So here bromine 1, then after 2, then after 3, and then after 4. So according to this atomic number 1, 2, 3, so it is coming anti-clockwise. So anti-clockwise it is S configuration. Means this Fischer means 3D molecules, its representation in Fischer projection, and that its naming or configuration naming which we are giving S according to CIP rule. Here that less priority fourth atom is there in vertical line, so no need to flip the answer. Next coming here we can see that here 1 chlorine atomic number highest, then after oxygen, then after nitrogen, and then after hydrogen. So 1 2 3. So 1 2 3 like this, 1 2 3. So 1 2 3 is coming clockwise, 1 2 3. So as it is coming clockwise, and since that list priority is there in horizontal line, then change the answer. Clockwise is R, but it will be S. Similarly to this Fisher projection where two chiral centers are there. So in this we can see that this chiral center where atomic number 1, then after this 2. Why? Because this carbon is connected to next carbon, whereas this carbon is connected to hydrogen. So 2, then after 3 and 4. So 1 2 3 it is coming anti-clockwise. So as it is coming clockwise means it is R, but since list priority is there on horizontal, then we will consider R as a S. Similarly, this chiral center which having priority as 1, then after this one 2, then after 3. So 1 2 3 is coming clockwise, anti-clockwise, correct? So as it is coming anti-clockwise, so it will be what? S. And here vertical on list priority is there on vertical line, so no need to change the answer, it will be S. Means both are SS configuration, both are SS. Means if this one is rotating light anti-clockwise, means this will also rotate light anti-clockwise. Next, this one, if this molecule, here we can see here we cannot check plane of symmetry, right, and center of symmetry. So by configuration also we can come to know whether it is optically active or inactive. Clear? Like once again revise this one. Here absolute configuration means that 3D arrangement of group of molecule containing asymmetric carbon. Asymmetric carbon means chiral center is termed as absolute configuration. Clockwise if it is rotating, then it is called R, and if it is rotating anti-clockwise, then it will be S. So how we can come to know? By applying CIP rule. So by CIP rule, that this all those we came to conclusion. Next, moving further, now here that this molecule, so here it having again 1 2 3. So is moving clockwise, is moving clockwise or anti-clockwise, but hydrogen is there in horizontal line, so S will be R, whereas this one will be, as it is coming clockwise, so R will become S because hydrogen in vertical line, horizontal line. So both are like here R and S, means they are doing internal compensation, means that optical light will be compensated by both of them. Now moving further, so this is the configuration naming as well as telling the optical behavior also. Now moving case 2, dash wedge representation. So in dash wedge representation, if hydrogen, if that list priority is on that dash line, then no need to flip the answer like here. Bromine 1, then after oxygen 2, and then after carbon 3. So as it is rotating clockwise, so it will be R. But if it is there on wedge, then change the answer. Like here 1, then after 2 and 3. So as it is moving anti-clockwise means S, change the answer to R. And if it is there in plane, not on dash and wedge, supposing given plane only, that plane, if it is there in plane that atom or group of atom, then make the even exchange. Make the even exchange means this atom if you are exchanging with this, then this one you exchange with this, and then after see its configuration. So configuration here that H is there, D is there, Br and OH. So if fourth atom we can see here hydrogen is there, so it is there in plane, so we need to do even exchange. So hydrogen is coming here, bromine going there, OH is coming here, deuterium coming here. So on behalf of this we can see that now it is 1, then after 2, then after 3 and 4. So it is 1 2 3 is coming, 1 2 3 is coming anti-clockwise, so it will be S. If we will do only odd exchange, then again we have to change R into S. Next, moving amine inversion. Amine inversion is what? At room temperature only, that it will fluctuate. Its a structure will fluctuate. Like if tetra alkyl ammonium ion is there, that will be stable because it is A, B, C, D all are different. So it is optical isomer and its mirror image are enantiomers. Its mirror image is enantiomer and it will show optical isomerism. It will show optical isomerism. And if R1, R2, R3 and R4, if all are different, then it is called optically active also. It might be that if it having that enantiomer, then in solution, if it is rotating light clockwise, so this will rotate anti-clockwise. So overall racemic mixture will be, that we will study now after this, that racemic mixture will be optically inactive, but this particularly is optically active. Next, moving, that chiral nitrogen containing either tertiary, primary or secondary amine do not show optical isomerism. Why? Because this is always fluctuating, means it will change. So at room temperature you can see this R3 is coming here and R1 is coming here, so this is called amine flipping, and due to that it is not showing optical isomerism because it's a structure only, not fixed. So next, moving further, relation between only one chiral atom when it is present, that compound when it having only one chiral center is present, then what is the relation between compounds? So they will be enantiomer. What is the enantiomer? They are a non-superimposable mirror image of each other. Like here this one you can neglect. So here we can see that this one is that P mirror image is Q, so it is enantiomer. P and Q are enantiomer. So like here we can see that this molecule, so this is one chiral center, so its mirror image is this one. Both are enantiomer, means both are optically active. Means if we'll see that by RS configuration, which RS configuration is telling the nature as well as optical property also. So on behalf of that, like here 1, then after 2 and then after 3. So 1, 2, 3 as it is moving clockwise, so means it should be R but it is S. And similarly we can see this one, so 1, then after 2, 3. So as it is coming anti-clockwise, means S will become R. So here you can see this is S and where this is R. So both optical properties are opposite to each other, both are optically active. So enantiomer means if that compound is there, so that compound will have enantiomer. Means if suppose in organic solution, that in polarizometer, if this compound is there, means its enantiomer also will be there, because this is one possible product, so there could be possibility of this product also. Means both will be, if 50-50%, in that case that mixture is called racemic mixture and that mixture will be optically inactive even though they are optically active. So once again try to understand, this A and B is there. If both A and B, if percentage is 50-50%, then PPL light as it is entering and after coming also there will be no deflection. Yes, they both are deflecting PPL light, but this is deflecting anti-clockwise, so this one is deflecting clockwise. So overall due to that deflection is mitigated, it became null and void. But if their percentage is not 50-50%, then overall it will be not racemic mixture. It in that some percentage will be optically inactive, remaining percentage of mixture will be optically active, and that is only called optical purity of the substance, which we will study slowly after this. Optical purity means how much after that racemic mixture, how much that mixture percentage is optically active, means they can rotate light. Means if suppose in this they are 30-30%, So remaining, let's suppose this one is 70% and this one is 30%. So their 30% will be optically inactive. So it's remaining how much? 70, in that 30% gone means 40% overall in mixture compound will be optically active, and if this one is there means it will rotate light anti-clockwise. Understood? So that is called optical purity of the substance or enantiomer excess, that topic. So like here also we can see that this one is also chiral center, one chiral center, means this is 1 2 and here 1 2 3. So as it is moving clockwise means it should be R, but it will be S because vertical hydrogen. Means this compound is also optically active, means it will have enantiomer. It will have enantiomer. So let's suppose this is Fischer projection and this is its dash wedge representation, and it is coming R, and both molecular formula is same. So yes, both are enantiomer. If they are, again I am telling, if their percentage is 50-50%, then only overall their mixture will be 100% optically inactive. Otherwise, if their percentage is not 50-50%, then remaining which is there in excess enantiomer, that will be optically active. Overall mixture will be optically active. Next, moving further, this we discuss relation between when molecule or compound having one chiral center. Now, if molecule having more than one chiral center, then in that case what will happen? Either it will be enantiomer or identical, means meso compound, or diastereomer. So in enantiomer we know that non-superimposable mirror image of each other. Identical also we know meso compound, it will have plane of symmetry. Diastereomer means which is not superimposable and not mirror image. So like here this molecule is there, so it molecule having two chiral center and it having plane of symmetry also we can see, whereas this molecule not having plane of symmetry, right? This OH is this side, this OH is this side. So this is meso compound, identical, whereas this one is not identical. Means it will have mirror image, and that mirror image will be either enantiomer. If that is having mirror image means that will be enantiomer, and if it's not mirror image and not superimposable, then it will be diastereomer. So always remember, if any molecule having diastereomer means diastereomers, two different entity, so their dipole moment will be different, melting and boiling point will be different, solubility will be different, density will be different, a specific rotation alpha will be also different. But if enantiomer is there, so enantiomer is just mirror image of each other, means only their optical property is different, remaining all those physical properties will be same. So here we can see for enantiomer all physical chemical properties same except two. They will rotate ppl to same extent in opposite direction, and if their percentage, once again I am telling, if their percentage in mixture is same, then overall mixture will be optically inactive, otherwise not. And they react with optically active compound with different rates. Means enantiomer reacts with optically active compound, but their rate of reaction will be different. And this one, that they will rotate with same extent but in opposite direction. So only this two properties different, remaining all properties are same. Like here we can see that this example, so this having more than one chiral center, so here Cl, here ethyl and methyl, so here no plane of symmetry. So this compound here also we can do CH3. So now we can see here it not having plane of symmetry, so it is not meso compound. Here also plane of symmetry is not there because ethyl and methyl is there. So these two are, if we'll see here Cl means mirror image of each other, right? So this both are enantiomer. Similarly here this one CH3 CH3 and ethyl is there, but here hydrogen and here hydrogen is there, but here hydrogen chlorine and chlorine hydrogen. Means these two are molecular formula, structural formula is same. A structural formula means their IUPAC is same. What is different? They are not mirror image and they are not superimposable on each other. Means that compound is called diastereomer. Means their melting point, boiling point, dipole moment, all those specific rotation, density, everything will be different because they are two different geometry. So these two are different. Means 1 and 2 is enantiomer, 1 and 3 is a diastereomer. Next coming 2 and 3. So 2 and 3 is also like here Cl is there, here HCl is there. If it is mirror image means this HH should come here, HH. So this both are diastereomer. Similarly 3 and 4. 3 and 4, so here chlorine and hydrogen is here, chlorine and hydrogen, and this hydrogen and chlorine is here. So both are mirror image, non-superimposable mirror image of each other, means they are enantiomer. Whereas 2 and 4, 2 and 4 again diastereomer, 1 and 4 is again diastereomer. If this molecule is given, 2 chiral center again, but it having, you can see, plane of symmetry. So overall this molecule having chiral center, so chiral center is 2, but this is called achiral molecule or optically inactive, and its mirror image, because this both are having both are optically inactive, so both are same only, both are identical, because if it is rotating light overall, suppose this is rotating with R, and if it is rotating R, so this will also rotate R and R only. If it is RS, so this will be also RS. If it is S and R, so this will be also S and R. Means for meso compound, since it having plane of symmetry, so there is no sense of its optical activity because its optical activity is already diluted. Means how? If it is rotating light clockwise, then it will rotate anti-clockwise. Let's study this one. Like here applying CIP rule. So highest atomic number 1, then after this one is 2 because carbon connected to oxygen, whereas here carbon connected to hydrogen, oxygen and carbon. So this is 2, and then after this one is 3. So how it is coming? 1, 2, 3. So it is coming anti-clockwise. So if anti-clockwise means this is coming S, but we will consider this one as a R, right? And similarly here 1, then after 2, and then after this is 3. So this is coming 1, 2, 3, 1, 2, 3 like this clockwise. So if it is clockwise means it will be R, so we will change into S. So you can see here if this is rotating clockwise means this way is rotating anti-clockwise. Configuration is telling its optical behavior. So as if it is rotating clockwise, this is rotating anti-clockwise, so overall this molecule is optically inactive. So that only this symmetry also telling plane of symmetry. If it is having plane of symmetry, it is optically inactive. Means its mirror image also will have same optical property, means there is no change. So both are identical. But if that compound does not have that plane of symmetry or symmetry element is not there, means that will be optically active. Means diastereomer and enantiomers are optically active entities. Yes, enantiomer, if they are 50-50%, 1 and 2 both are enantiomer. If their percentage is 50-50%, in that case they are optically inactive mixture, but individually they are optically active. So enantiomer entities and diastereomer entities both are optically active, whereas those molecule which is showing meso compounds, they are due to their internal compensation. If one is rotating R, so another is rotating S, so it will be 0. Clear? Now coming to here, stereoisomerism of tartaric acid. So tartaric acid is this one, so its mirror image is this one, whereas this one is not mirror image. Here it having, you can see that plane of symmetry. So this is optically inactive. It will not have mirror image because both will be identical, because their property, optical property, will be same. Whereas this both are mirror image of each other, means they are enantiomer. So this is the stereoisomerism of tartaric acid. Means stereoisomerism means molecular and structural formula same, only their optical activity will be different on behalf of their orientation and geometry. So next, meso compound or mesoisomer is what? It will have achiral compound. Achiral compound means not that it does not have chiral center. Yes, it having more than one chiral center. So achiral compound which having chiral centers is known as meso compound. It is achiral means optical rotation overall 0. Alpha is 0 due to internal compensation, and they are distereomers, means DL pair, so that they have different physical properties than DL pairs. What is telling that they are distereomers of dextrorotatory and levorotatory. Like here, that this one is this is, suppose this enantiomer. So if it is dextrorotatory, so this will be levo. So overall they will compensate, external compensation. If 1 and 3 we will see, so they both are diastereomer. This both are diastereomer. Like that we discuss in geometrical isomerism also. Cis and trans, their molecular formula is same, a structural formula is also same, means IUPAC is same. Only there that optical activity is different, means they are diastereomer. Cis and trans are also diastereomer, means they are not mirror image of each other. Cis and trans are not mirror image of each other, then that's why it is called diastereomer. So similarly here also meso compound is also diastereomer of their respective enantiomeric pairs. Next, that presence of more than one asymmetric carbon only, then only meso possibility, and they are non-resolvable. Non-resolvable means they cannot be separated, means meso isomers cannot be separated because they are having same, they are identical. So like here, which of the compound is meso or not? So like here, 2 chiral center and it is even ring, so we will check plane of symmetry. If it is there, then it will be optically inactive. If it is not there, then we will go for COS. So like here, plane of symmetry is there. So even though it having 2 chiral center or achiral center, overall molecule is achiral or optically inactive. So this is meso compound. Here plane of symmetry is not there and neither center of symmetry there. So this is optically active. This compound is not your meso compound. Similarly here bromine, so it having plane of symmetry, optical. Only we have to check meso compound. This one also not having plane of symmetry. So this is also not meso compound. So for meso compound, chiral center should be more than one and should have plane of symmetry. If it is not there, then we will go for center of symmetry. So like here in this molecule, we can see how many chiral center, more than one, 3 chiral centers are there, right? And here plane of symmetry is there because this atom will be cutted half and half. So overall it having plane of symmetry. So this is having meso compound. This center is only called pseudochiral center. Now coming to here, that here also plane of symmetry is there, and plane of symmetry, why? Because OH is here, OH is here. This OH and H will be cutted half and half, so it having plane of symmetry. So this both are meso compound. Even though it having 3 chiral center, overall this molecule is achiral. Here this is also overall this molecule is achiral, means meso optically inactive. Now coming to racemic mixture. So enantiomeric pairs are called enantiomeric pairs are called racemic mixtures if they are equimolar. So equimolar of 2 enantiomers pairs are called racemic mixtures. Enantiomeric mixtures is always optically inactive due to external compensation, means if it is rotating clockwise, so this will rotate anti-clockwise. Overall that mixture will be optically inactive. And each enantiomer, by the way, is optically active, means it is rotating PPL light with certain extent, and that their direction we can understand without putting in that polarizometer, just by applying CIP rule, which is telling its configuration. So both are enantiomer, both are optically active, but their racemic mixture equimolar, optically inactive. Next, coming to resolution. To separation of enantiomer, let's suppose an organic compound solution is there, means it having enantiomers. What is there? Enantiomer. So that separation of enantiomer from racemic mixture is called resolution. So we know that enantiomer having all physical and chemical properties same, except only one thing, that rate of reaction will be different with optically active compound, and second is that they will rotate light same extent only but in opposite direction. So how to separate if their melting and boiling point is same? We cannot do fractional distillation. So for that we will make it diastereomer. Like here, suppose for example this both are enantiomer. So we'll do reaction with this compound. So here this carboxylic acid and here this OH. So we know that carboxylic acid is more acidic than OH. So here like acid base reaction will happen. So if this configuration is S and this is R, so this is becoming S and R, whereas this one is R combining with R, so it is becoming R and R. So now this both are diastereomer, and diastereomer all physical properties are different. So now their boiling point is different, so now we can separate by fractional distillation, and after getting into different container, again if we will do hydrolysis, then we will get this compound in separate container. So this process is called resolution, means if any compound is there, means if compound is showing enantiomer, means what? If suppose that this compound when it is formed, when this compound is formed, so that both possibilities there, means either product will be formed in this way or either product will be formed in this way. That's why these two entities are existing in that solution, and that is only called enantiomer. If their percentage is 50-50%, that will be racemic mixture, and if percentage they are not 50-50%, then overall solution will be optically active. So here that racemic mixtures, since this both are due to external compensation optically inactive and their melting and boiling point are same, so cannot be segregated. So we'll make their respective diastereomer, and then after we can segregate, and after hydrolysis again we can get it back in two different container, this two. So that process is called resolution. Next, moving further, optical purity or enantiomer excess. As I told, that is not 100% sure that always that both compound will be always 50-50% enantiomers pair. Means if suppose one is 70% and another one is 30%, so 30% is neutralizes each other by external compensation, their optical activity, but remaining one which is 70%, its remaining 40% is optically active. So that how to calculate its optical purity? Observed optical rotation divided by optical rotation of pure enantiomer in 200. So here example also given, so you can go through this example. Moving further, next naming for that Fisher projection after RS configuration, DL configuration. So that RS configuration is absolute configuration, is telling its optical behavior, whereas DL, this capital D and capital L is just name, IUPAC naming, is nothing to do with dextrorotatory and levorotatory. But R and S having to do with D and L, means dextro and levo it can tell. Means if it is rotating clockwise, rectus means dextrorotatory, and if it is rotating anti-clockwise means sinister, means it is a small l. But this is just used for the IUPAC name, it is used for its naming, whereas RS is we can use as a naming also, but along with that it is telling its optical behavior. So like here, if OH highest priority, only two is there, one is OH is there and one is amine system is there. So if alcohol, if it is there right hand side, then it is called capital D, D-glyceraldehyde. And if it is left hand side, then it is L-glyceraldehyde. If more than one OH is there, then lowest OH direction, like glucose we discuss. So if it is a right hand side, then it will be D, and if it is left hand side, that lowest down one, so that one is called L. Similarly for amine also, if amine is right hand side, so D, and if it is left hand side, then it will be L. So here we need to little bit correct. Here it should be left hand side, student. So this one. Clear? Next. In case of more than one chiral center, always we will go for the lowest one. So this one is the lowest chiral center. This is not chiral center. So lowest chiral center OH will determine its nature. So this is D-glucose. Remember, its mirror image will be L-glucose and both will be enantiomer. Clear? Next, moving further. Next, naming for the Fischer projection, erytho or trio. So erytho and trio is what? Erytho and trio is what? That if same groups are same side, then erytho. If opposite side, then it will be trio. So this one is erytho, whereas this is trio. Now last topic, calculation of optical isomerism. So if molecule is unsymmetrical, always total isomer will be 2 to the power n. N is the chiral center. So meso compound will be 0, and racemic mixture from this will be optically active divided by 2. Like here we can see, if compound is unsymmetrical, like here no plane of symmetry is there, here CH2OH, here CHO. So total will be 2 to the 4. So optically active 4 structure, optically inactive meso will be 0, and racemic mixtures will be 2. Means 2 enantiomeric pairs. Like here we can see that same molecule CHO, CH2. So HOH, HOH. So is not having plane of symmetry. Similarly, means is not having plane of symmetry. Similarly, here also we can see plane of symmetry is not there. So this mirror image is this enantiomeric pair. Similarly, here also plane of symmetry is not there. So this mirror image is this. So two enantiomeric pairs. If we'll tell this one and this one, so both are diastereomer. This one and this one diastereomer, like that. So total 2 enantiomeric pairs are there, means 4, and meso is 0. If molecule is symmetrical and chiral center is even, then formula like geometrical isomer 2 to the power n minus 1 plus 2 to the power n by 2 minus 1. So 2 to the power n minus 1 is telling about optical active molecules, means it will show in enantiomers and all, and 2 to the power n by 2 minus 1 is telling meso compound, means number of chiral center. N is here number of chiral center. Like here we can see that this molecule CHO, CHOH, CHOH and CH2OH. So it having no plane of symmetry, and along with that, so what is the case? Molecule is symmetrical and N is even. So here we can see that if this molecule is symmetrical, means here it should be CHO only. So here we will change this one. Instead of CH2OH, it should be CHOH. So here this will be CHO aldehyde. So now it having plane of symmetry, so it is symmetrical, and total chiral center is even. So total isomer will be 2 to the power n minus 1 plus 2 to the power 2 by 2 minus 1. So overall 3. In that optically active will be 2, meso will be 1, racemic mixtures will be 2 by 2 means 1. 2 by 2 means 1. So overall 1 meso compound and 2 optically active means enantiomeric pair. So like here we can see this one is the 1 meso compound and these 2 are optically active racemic mixture. Next coming, if molecule is symmetrical and n is odd, then total optical isomer 2 to the power n minus 1, meso 2 to the power n minus 1 by 2, and optically active will be optical isomer minus meso, that will be optically active compound, and racemic mixtures will be optically active compound divided by 2 in enantiomeric pairs. So like here we can see that 3 chiral center and molecule is symmetrical, plane of symmetry is there. So total optical isomer, how many? 2 to the 4, and meso compounds are 2. So optically active compounds are how many? 4 minus meso is optically inactive. So total optical isomers are 4 minus 2, so it will be 2. So racemic mixture is 1. So here we can see this molecule. So 1 is that plane of symmetry, means meso compound. This one also meso compound. So these two are meso and these two are optically active, means enantiomeric pair is 1, racemic mixture is 1. Clear? Next, if molecule is unsymmetrical, like we discussed, so total, if we are calculating stereoisomerism, so in that we will consider its geometrical center also and chiral center also. Till now we discuss chiral center. So let's suppose, for example, chiral center, this one is the chiral center and geometrical center. So total stereoisomer will be 2 to the power n. So 2 to the power 2 is 4, as in starting also we discussed. Next, here how many chiral centers? N value 2. So stereoisomer will be 2 to the 4. Similarly, here if geometrical and chiral center both there, so how many stereoisomer? Including 3 means 2 to the 4, 4 to the 8. Next, here on this question, how many stereoisomer can exist for the following compound? So we know this one is the pseudo chiral center, but still we will consider this one as a chiral center. So total how many chiral centers? 3, and it is having symmetry there. Symmetry is not there. So overall it will be 2 to the power n minus. Clear? So here actually little bit, how many here chiral center? 3, and it is symmetrical. So odd chiral center, and along with that here also we can do CH2, actually carboxylic acid. So this one also will come here H. Now we can see that yes, 3 chiral center and it is odd species, means 3 chiral means odd and it having plane of symmetry, means symmetrical molecule. So total isomer 2 to the power n minus 1 means 2 to the power 3 minus 1, 4. Clear? But due to this pseudo chiral center, 4 minus 1, it will be 3, because 1 will be meso. So optically active will be 3, including 1, total will be 4. Okay. So thank you very much. Now revise this all those properly, and then after solve some related questions also. Thank you very much.